This evening, I'd like to welcome Professor Martin Hendry. He is the Professor of Gravitational Astrophysics and Cosmology at the University of Glasgow, where he is also the Clerk of Senate and Vice Principal of the University. He is a senior member of the LIGO Scientific Collaboration, the global team of more than 1,500 scientists who, with their colleagues in the Virgo collaboration, made the first ever detection of gravitational waves, the discovery awarded the 2017 Nobel Prize for Physics. Martin is also a Fellow of the Institute of Physics and is also a Fellow and currently the Vice President of the Royal Society of Edinburgh, Scotland's National Academy. He is a passionate advocate for science, education and communication. In 2015, he was awarded the MBE for services to the public understanding of science. Will you join with me in giving Martin an experience with the National Society? Thank you and welcome.
Thank you very much, everyone. So, of course, at this time of year, it's always a bit of a hostage to fortune travelling in the UK. So it's maybe just as well that we'd arranged for this to be online. But I'm sorry I'm not with you there in person to meet you in 3 dimensions, so to speak. I hope that IT won't let us down. I've generally got a good Wi-Fi signal at home. So do let me know, however, if I'm not coming through loud and clear. And in particular, if you're not seeing and hearing the various multimedia and animations that I'll be showing during the talk. So Paul's already really covered this, but I thought I would just put in a slide to say a bit about who I am and where I am based. Well, you can see from my backdrop the very splendid Gilbert Scott building, the sort of neo-Gothic architecture that is the main building in Glasgow University. So here's a few more photos of Glasgow in a variety of sky conditions, none of which quite as grim as the -7 we're experiencing tonight. So I'm, of course, here mainly with my Professor of Astrophysics hat on. The university-wide role does occupy a great deal of my time, but I very much relish the opportunities to escape from that and to talk to students and colleagues about our astrophysics research. And as Paul described, I'm mainly going to be talking about the history to date of this exciting new field of gravitational wave astronomy, but a little bit in the context of how we are beginning already to use gravitational wave observations to say something about cosmology, the study of the universe on its very largest scales, addressing such questions as how fast is it expanding, and indeed will we still see it continue to expand in the future. The tools that we have to do that are compact binary systems, pairs of black holes and neutron stars, or indeed even one black hole and one neutron star, which we are now able to observe colliding, and in so doing, they give off gravitational waves, which are ripples in space-time produced by those violent cosmic events. So I'm going to begin my talk by just a little bit of a gentle introduction into what we mean by gravity and gravitational waves in the context of Einstein's general theory of relativity. But again, don't panic. It's not going to be detailed with lots of maths and equations. I mean, really none at all. I'll just focus on a sort of big picture introduction to what general relativity is all about. And that's to give you some context for just what a challenge it is to detect gravitational waves and why it essentially took us 100 years between Einstein publishing the theory and developing the technology that was capable of detecting these space-time ripples. But I'll try and devote the bulk of my talk to what we've done since that first detection back in 2015. It was announced in February 2016. What it's told us about the universe and what the prospects are for the future as this new field of gravitational wave astronomy really gets up and running. And I guess while I'll focus in large part on some of the cosmological questions that gravitational waves hopefully will help us to answer, questions about dark matter and dark energy, that kind of thing. There's a broader landscape of areas of astrophysics where gravitational waves we think will have a role to play, including more questions about the fundamental interactions in physics, the nature of gravity itself, how it fits in alongside the strong and weak nuclear force and electromagnetic forces. And, again, this is a field that gravitational waves is already contributing to, and we would hope will continue to do so in the years to come. So I'll end my talk by focusing on some of the upcoming exciting missions and ground-based facilities which are in various stages of planning. Now, gravitational waves are not electromagnetic waves. Let me say that from the outset, just in case people weren't clear about that. The visible light that our eyes can see, and which were the domain of telescopes for centuries, well, over the last 100 years or so, we've expanded that way of probing the universe beyond the visible spectrum considerably to both radio waves at one end and X-rays and gamma rays at the other. And altogether, the electromagnetic spectrum is now a really excellent way for us to understand a whole range of phenomena in the universe, using a mixture of impressive ground-based facilities and space-borne satellites. But general relativity predicts a whole new window in the form of gravitational waves. These are not electromagnetic waves, they're a different spectrum of radiation altogether. So in the coming slides, we're going to talk about what exactly they are and how they came about in our developing understanding of gravity in the early decades of the 20th century. A lot of that is going to be to do with the work of Einstein, and Einstein is, if you like, a bit of a scientific hero of mine. This is a photo of me sitting on the statue of Einstein at the National Academy of Sciences in Washington, DC. It's a few years since I was last there, but I always like to go visit the statue when I'm there. A bit of a pilgrimage to Einstein's statue. And again, as I said a moment ago, this is not going to be a talk full of equations, although I like the sculpture very much. I suppose for most people going to visit it, they're probably scratching their heads when they look at the equations engraved there, and at least the first two, but maybe the third one isn't quite so unfamiliar. It's the famous E equals mc squared. So I'm hoping that you are at least a bit familiar with that, the idea of energy and mass being equivalent, one of the key ideas of Einstein's special theory of relativity that he published in 1905. And the c in E equals mc squared is the speed of light, which is 300,000 kilometers per second, so a very big number, and consequently E equals mc squared is basically telling us that even a small amount of matter in principle contains a vast amount of energy, because you're multiplying by that big number c squared to get the equivalent number of joules to even 1 kilogram of matter. So we'll come back to that in a little while, because that, I think, is an equation that gives us some insight into this amazing new world of gravitational waves that we're just beginning to open up. So gravity in Einstein's universe is an evolution, a development beyond the ideas of gravity that we get from Isaac Newton. It's not to say that Isaac Newton's theory of gravity is completely useless. It's perfectly adequate for most everyday circumstances. It talks about gravity as a force between massive bodies and allows us to calculate what kind of accelerations you'll get when a certain amount of mass is acted upon by a certain amount of gravitational force. So the equations that govern Newton's theory of gravity are basically fine to let us work out how to send spacecraft to the moon and back, for example, or even further within our solar system. But as we look in the universe on larger scales, or as we try to understand gravity in more extreme conditions, then we begin to realise that Newton's theory is not the full picture. And that's what Einstein was wrestling with in the early years of the 20th century. He had problems with Newton's idea of gravity as a force because, well, the force was supposed to act instantaneously between massive bodies. You know, the force of gravity between the Earth and the Moon, according to Newton, really was an instantaneous action of the Moon on the Earth and vice versa. And Einstein had a bit of a problem with that. He basically struggled to see how the force could reach out through empty space between the Earth and the Moon, or the Earth and the Sun, and so on. So he really took the idea of gravity back to square one and redeveloped the whole notion in terms of gravity not as a force, but as a curving, a warping of space-time itself. Now, this is an analogy that maybe you've been thinking about or talked about before. It's the idea of, well, taking a big stretched sheet of rubber like a giant trampoline and dropping a massive body like the Earth onto that. It will cause the trampoline to curve, to bend, just like you're seeing here. Now, it is just an analogy. It's a far from perfect one, because, of course, what we're talking about in the real universe is 3 dimensions of space and 1 of time, whereas we're reducing that just down to a 2-dimensional analog to show you the idea of the warping of space-time. But I think it serves us quite well. It gives us at least something to hold on to in terms of what the effect of that space-time curving will be. Because just as you can see in the analog picture, in the region of the Earth, bodies will follow a different path due to the curvature of space-time. So the reason that the Moon orbits the Earth in Einstein's theory isn't so much because there's a force reaching out from the Earth to the Moon, as Newton would have us, but instead that the Moon is just following the natural curved contours of the space-time in the Earth's vicinity. A bit like how you might roll a marble around such a kind of curved, warped fabric of a trampoline or the like. And there's a neat phrase attributed to John Wheeler, an American physicist that was around at more or less the same time as Einstein, maybe a little bit later. And John Wheeler said that gravity in Einstein's picture was all about space-time telling matter how to move and matter telling space-time how to curve. So there's a fundamental connection between the curvature of space-time determining how matter will move, as I was saying before, like the Moon following a curved path around the Earth. And then it's that very presence of matter that generates the space-time curvature in the first place. So that's in just a few minutes an attempt to try and give you a sense of what Einstein's theory of gravity is all about, without any complicated equations to get in the way, but just a simple picture of the curving of space-time like on a bending trampoline. So gravitational waves are what happens when that space-time curvature is changing. So if we think of, say, 2 massive bodies orbiting around each other, what that is doing is changing the curvature of the space-time fabric all the time. And what that will produce, according to Einstein's theory, is ripples in the fabric of space-time that will spread out from those massive bodies all through the universe. That's what we call gravitational waves. And they're caused by changing gravitational fields, just like you can see is happening here as the 2 massive bodies. Think of them as like neutron stars or black holes. That's mainly what we're going to talk about in a few minutes. As they're orbiting around each other, they're shaking up space-time and causing these ripples to spread out. And that really is where lies the rub, because the space-time ripples produced by an event like that, 2 neutron stars orbiting very closely around each other, they are very weak by the time they reach us. The ripples, again, our analogy here is to think of like ripples spreading across a pond. And by the time they reach us, as they spread out, then the disturbance in our local patch of space-time is incredibly tiny. It's equivalent to about, well, if you take, say, a hair on your head, about 1 millionth the width of one of those hairs, or about 1,000th the size of a proton, the particle in the nucleus of an atom. So how on earth are you going to measure a disturbance in space-time as small as that? Well, how on earth is the operative words, because the Earth shakes, and that would swamp the signal we're looking for, especially given that it's so tiny. So it's a real challenge, given all the local disturbances going on in our Earth environment, to detect the changes in space-time curvature caused by a gravitational wave passing by. And yet, remarkably, that's what we can now do. The instruments that were responsible for that first detection of gravitational waves 10 years ago are called LIGO, standing for Laser interferometer gravitational wave observatory. And as we heard in Paul's introduction, for many years I've been a senior member of the LIGO collaboration. Until quite recently, I was one of the division heads of the global collaboration. I've stepped back from that role because of my wider university responsibilities now in Glasgow, but still very much involved in the ongoing analysis of the data we get from the LIGO detectors and planning for future observing with LIGO. Just to confuse matters, I'm actually wearing my sweatshirt from the other collaboration I'm part of, which is called the LISA Consortium. LISA stands for Laser Interferometer Space Antenna. So that's another project altogether. And a bit later in my talk, I'll say a bit more about LISA. But for now, let's concentrate on LIGO. There are two LIGO sites, one in Livingston, Louisiana, shown in the top right, and the other in Hanford, Washington State, in the lower left. They're 3,000 kilometers apart, and they're really vast facilities. The arms of LIGO, they're L-shaped. Those arms are 4 kilometers long, and they're the most sensitive scientific instruments ever built. So what exactly do they do, and how do they help us detect gravitational waves? Well, kind of the clues in the name. It's all done with lasers, and it's all done using interferometry. So what that is all about, I'm going to try and explain in this slide. What we see in the lower left is a little cartoon animation showing laser light inside a kind of cartoon representation of the LIGO detector. So what we see is the laser beam being split into two, and the two beams go off at right angles to each other and bounce off mirrors at the ends of the arms. And then as a gravitational wave passes by, it will stretch and squeeze our patch of space-time, albeit by that really tiny amount that we said before. But what in principle that will do is change the path length that the two laser beams travel along. And because we are bouncing the laser light off the mirrors, when it comes back to the central beam splitter and then is passed out to the detector on the right-hand side of the animation, what we can look for is a change in what we call the phase of the laser light, which really just means the peaks and the troughs of the two waves getting out and in and out of step with each other, because the path that the two beams are traveling is changing ever so slightly as a result of the gravitational wave. So to measure such a tiny change as a millionth the width of a hair requires very long arms, the 4 kilometers long, but also requires super precise knowledge of the wavelength of the laser light, but also requires us to bounce the light back and forth hundreds of times in the arms. So again, the cartoon is a great simplification of what's going on, but the essence of it is really what happens in LIGO, that we look for changes in that interference pattern of the two beams, changes in the phase of the light coming from one arm versus the other arm, and that pattern of interference will change in a very well-defined way when a gravitational wave passes by. We'll see the detail of that on the next slide. The animation on the right-hand side, it's not there to try and hypnotize you. It's basically, again, just showing this idea of the arms stretching and squeezing as a gravitational wave passes by. In this case, the gravitational wave would be coming out of the screen towards you. But of course, the amount by which it changes, the arm lengths change, is incredibly tiny. So I mentioned before the millionth the width of a hair. Well, another way to represent it is if you take that same hair and compare its width with the distance from the solar system to Alpha Centauri. That's the fractional change we're trying to measure. So it's, of course, incredibly challenging to do this. And it's challenging for a variety of reasons. First, it's in a very, very small effect, but also it can be swamped by other effects which are much larger in relation to changes in the local Earth environment, what we might term noise. So the background noise can overwhelm the signal that we're trying to detect. So one of the things that really helps isn't just having this incredible technology in the detector itself, but also having a very good idea of what the signal ought to look like. So that's what this slide is about. In the lower left, you've got an animation showing two black holes spiraling around each other. And analogous to what we were saying a few slides back, as the gravitational field changes, as they spiral in towards each other, then that's sending space-time ripples, the gravitational waves, outwards from the black holes. And what happens is the black holes will spiral around each other faster and faster as they get closer and closer together, and the gravitational wave signal will also get stronger. And that produces the pattern that you see in the graph. What you get is a kind of sine wave type pattern, but the waves are getting closer together. That's the frequency increasing. And then also it's getting stretched out in the vertical direction. That's the strength of the gravitational disturbance, the amplitude also increasing. And it reaches maximum strength roughly when the black holes merge. And then after that, you've just got one black hole, space-time wobbles a little bit more, things settle down again. So we get these three phases, what we call the in-spiral, that's on the left-hand side, the merger, and then the ring down as things settle down again. So breakthroughs in the 2000s and beyond gave us much deeper and more complete insight into the kinds of pattern of distortion, disturbance that we were going to be looking for. And that really helped to augment the improvements in the sensitivity of the detectors that were coming on the kind of hardware side. So it was a combination of theoretical progress and progress with the hardware as well. And maybe a good way to tie those ideas together is to think of, well, suppose you were in a very noisy environment here on Earth, somewhere like, say, a school canteen, because quite often I talk about this when I'm doing schools outreach talks as well. It's very hard to maybe hear yourself think with all that background noise going on, and you might struggle to even hear the conversation of the person on the other side of the table. But if you've got a good idea of what you think they're talking about, then the brain's actually pretty good at interpolating and sort of picking out the signal from the noise, of picking out the thread of the sentence that they're saying, even when there's a lot of background noise. So that's a bit like what we are doing when we carry out our gravitational wave data analysis. We've got a good idea of what the signal should look like, and therefore that helps us to extract them from the noisy background. Now, I called this talk Listening to Einstein's Universe. So maybe rather than talking about looking at signals, it's appropriate now to consider listening to them, because the range of frequencies of gravitational wave signals that the LIGO detectors are sensitive to correspond to frequencies that our ears can hear. Gravitational waves are not sound waves, but we can represent them as sound waves to give us a better way to get a handle on the pattern of disturbance that they represent. So in fact, the pattern on that previous slide, the in-spiral, the merger, and the ring down, we call a chirp. It's a very characteristic pattern where the frequency is increasing as the wavelengths get squashed up and the amplitude is increasing. And that chirp pattern is, well, we'll hear it in just a moment, because the first detection, we were able to represent it not just visually, but also in terms of sound. So that's coming up in a moment. So overcoming this challenge of all the background noise, of course it helps if you think you know what signals you're looking for, but there's nothing to beat reducing the noise levels as well. Imagine a teacher coming into that canteen and saying, shh, keep the noise down, folks. Well, that's kind of where we were round about 2010. Because what we had to do was to upgrade the LIGO detectors. They previously had been operating for several years, but had not yet detected any gravitational wave events because they were too swamped by background noise. But various upgrades were carried out between 2010 and 2015, and I'm very pleased to say that the UK played a major role in that, led by our research institute at Glasgow University. And among the key developments were to replace the steel wires that suspended the mirrors at the end of the 4-kilometre arms by silica fibres, glass fibres, that essentially don't shake so much. I mean, the steel fibres didn't shake much anyway, but they still shook enough to introduce enough background noise into the detector to make detecting the signals very much harder. But with the silica fibres, then the mirrors became more still, and therefore the background noise was less of a problem. The coatings of the mirrors were also improved to make them essentially reflect more of the laser signal, so that we were losing less of the laser signal as it bounced back and forth along those arms. So there's a lot of technical detail here that I'm really skating over, partly just through lack of time, but also, to be quite honest, because I'm not an expert in this side anyway, I take my hat off to my colleagues in Glasgow and in other institutes around the UK that led the fundamental material science research to improve the detectors in this manner. And this was the contribution of the UK that was adopted by the National Science Foundation, the leaders of the LIGO project, and allowed the upgrade of the detectors, the improvement of the detectors between 2010 and 2015, so that they could begin operating as advanced LIGO in September 2015. And this is what we heard. Let me just freeze it there. So I ran the animation a couple of times. What we're seeing is a visual representation of the signal that we detected, September 14th, 2015, but also representing it in sound. Now, it was just a short burst of gravitational waves that lasted less than a second. So what I'm first of all doing is playing that over and over and again, which I think makes it a little bit easier to hear what's going on. But the other thing I'm doing is shifting it to higher frequency, analogous to what we often do with visual images, where we show them in false color to bring out details that are otherwise a bit harder to see. So I'll play it again, and what you've got to listen for is, first of all, the low rumble of the instrument noise, and then there's almost, it's like a bit of a dull thud, which is the gravitational wave signal sort of rising above that noise. I think personally it's a bit easier to hear when I shift it to higher frequencies. You get more of a sense of that chirp pattern that I described before, and that's also represented visually by the upward sweep in the orange and the blue, LIGO Hanford and LIGO Livingston. That's showing the frequency rising and the amplitude getting bigger as time elapses. But look at the scale. I mean, this is just about 0.2 of a second that all of that happens over. So let me just run it a few more times to give you a sense of that. So this was our first gravitational wave detection, and let me say that we were extremely excited when this was detected. We knew that we had a ton of work to do to make absolutely sure, as best we possibly could, that this was truly a signal from the cosmos and not just some local disturbance or some flaw in the design of the detector. But it was so clear in the data that we were very much of the view that we'd really got something here. Over that 5 months between September and February 2016, we did a ton of work to first reassure ourselves that we truly had made a detection, but also to try to characterize what had produced that detection. And then in February 2016, we were able to announce that first discovery. The announcement was on February the 11th. This is the webpage from just a couple of weeks later. There was a huge amount of press interest. We were on the front page of more than 900 newspapers the following morning. So what exactly had we detected? Well, this is the signal now represented superposed on top of each other. So hopefully what you can first of all see, if you hadn't clocked it in the earlier slide, is that the Livingston and Hanford signals really look rather similar. And that was very significant because these are detectors 3,000 kilometers apart from each other, and yet they seem to be detecting a very similar pattern. So that was good reassurance from the get-go that this was something from up there and not just a local disturbance. But we had a whole battery of statistical tests to try and check that, which we duly carried out over the intervening months. And what emerged from that was reassurance that it really was a gravitational wave signal, and secondly, that it had been produced by two massive black holes more than 1 billion light years away. So our analysis allowed us to work out the distance and also the masses of the black holes. And well, in fact, I have a colleague at the Institute of Cosmology and Gravitation in Portsmouth, Laura Nuttall, and I'm just going to play a short video that Laura is narrating, which explains sort of more or less how we extract that information, the masses and the distance from the data. Again, just in cartoon form, but hopefully it will give you a sense of how it's done.
On the 14th of September 2015, one of these tiny gravitational wave signals was detected by LIGO. By comparing the signal to the predicted signal, scientists are able to find out more about the origin of the gravitational waves. To determine the mass of the black holes and their distance, we can compare with theoretical models. The parameters of the model are adjusted until the predicted signal matches up to the data. The closer the black holes, the larger the amplitude of the detected signal. The mass of the black holes can be changed. The lower the mass, the higher the frequency.
So we've got a distance of just over 400 megaparsecs. A parsec is about 3¼ light years, so that corresponds to about 1.3 billion light years. Or in other words, we were seeing something that happened a long time ago in a galaxy far, far away. I should say I'm a big Star Wars fan, so a couple more Star Wars references coming up. But again, we wanted to also work out the masses of the black holes. So what we see here is an animation that we actually showed in the detection announcement in February 2016 that's representing the two black holes as they merge. You can see the distortion of space-time, like the stretched rubber sheet that we talked about before, and we see the single black hole left behind. Let me just run it one more time, and we'll see that at the moment of merger, there's a burst of gravitational waves, just sort of rather colourfully represented by the red spike. And that is a lot of gravitational wave energy released in that moment. So we were able to estimate the masses of the black holes, and what we got was that before they merged, they had masses of 29 times the mass of the Sun and 36 times the mass of the Sun, adding up to 65, which was the value in that little cartoon that Laura was narrating a moment ago. But we could also estimate the mass of the black hole left behind, and that turned out to be only 62 times the mass of the Sun. So basically, in that small fraction of a second, the equivalent of 3 times the mass of the Sun had been converted from mass into gravitational wave energy. And that's where we can use Einstein's E equals mc squared to tell us just how much energy that is. And believe me, it's a lot. And it's released in a very short time, so we can next calculate that as a gravitational wave power, which is energy divided by time. And the bottom line is that the amount of gravitational wave power, or what we could also call gravitational wave luminosity, analogous to the luminosity in light that we see from stars and galaxies and the like, the gravitational wave luminosity from this event was equivalent to about 50 times the light power of every single star and every single galaxy in the entire universe. Now, of course, it didn't last for very long, but it gives us some insight into just how much energy is locked up in the fabric of space-time that we were not able to be aware of, to detect, or even, frankly, to be sure that it existed prior to the LIGO detectors picking up these space-time ripples. And the remarkable thing for me was that this huge release of gravitational wave power was not accompanied by any light whatsoever. We don't think that when black holes merge, any light is given off. So consequently, you could say that we're really probing the dark side of the universe. Told you I was a Star Wars fan. And in fact, that reminds me very much of something Darth Vader once said, which is you should never underestimate the power of the dark side. Well, he was talking about the Force, I'm talking about the universe, but I'm not going to argue with Darth Vader because I think that little calculation we did hopefully reinforces your view that the amount of gravitational wave power in the dark side of the universe locked up in the fabric of space-time really is mind-blowing. So this first event, of course, attracted a great deal of attention, as I mentioned earlier, and as we heard from Paul, it was awarded the 2017 Nobel Prize for Physics. So that was quite a lengthy introduction to the basics of how we go about detecting gravitational waves. In the second part of my talk, I want to focus on what's happened since and what's coming up in the future. So the next big milestone was in August 2017. That's when a third detector, Virgo, situated just outside of Pisa in Italy, joined our global network. It had been upgraded to Advanced Virgo in a similar manner to how LIGO had been upgraded. And having 3 detectors was really useful because when you've only got 2, you can measure how far away the source is, just as Laura's video described, but pinpointing where it is in the sky is really quite a challenge. The way that that's done is by making use of the arrival time of the signal at the different detectors. But what that gives you is a kind of ring on the sky, which would all points in that ring would have the same delay time in the arrival of the signal between one detector and another. So LIGO Hanford and LIGO Livingston, denoted by the H and the L, there would be a ring on the sky denoted by the red ring in my diagram there, where the time delay would be the same for all points in that ring. If you're interested, the reason why you get that is all tied up with all that nasty trigonometry you probably learned about at high school, sines and cosines and all of that stuff. So basically, with only 2 detectors, you can't pinpoint the sky position terribly well. But with 3, you get 3 different pairs corresponding to 3 different rings on the sky, each with the same delay time. And where those rings intersect, well, that's where your signal's coming from. So that's the ideal case. How does it work in practice? Well, we didn't have too long to wait, because by mid-August 2017, August 14th, we had a black hole binary merger detection that was much better localized on the sky to about 60 square degrees compared with more than 600 square degrees for the events we detected up to that point, including the very first detection that we've been discussing up until now. So that new event, GW 170814, is shown in the lower left there, and because it was observed by all 3 detectors, we pinpointed the sky position much better. And we only had to wait 3 more days before the advantage of this global network of 3 detectors paid off again, because on August 17th of that year, we detected, this time not the merger of 2 black holes, but 2 neutron stars. So this was a remarkable new discovery, because for the very first time, in fact, actually the only time to date, we observed an event in both gravitational waves and across the electromagnetic spectrum. So here's what that signal sounded like in gravitational waves. And then less than 2 seconds later, the ping corresponded to the arrival time of a burst of gamma rays that was detected by NASA's Fermi satellite and also ESA's Integral satellite. Now, we think that delay time is because the gamma rays set off about 1.7 seconds later, that it takes short time for the kind of gamma ray burst to, gather momentum and sort of build up a head of steam after the initial burst of gravitational waves. But even if we just leave that as something we've got to kind of test observationally, if we keep an open mind as to whether the speed of gravity and the speed of light are the same, this was an event about 140 million light years away. So if gravity and light only got out of step by about 2 seconds over 140 million years, that tells us that the speed of gravity and the speed of light must be almost identical. Einstein's theory says that they should be exactly the same, but now we've got observational evidence to tell us that they have to be incredibly similar to each other. We're constraining the difference between the speed of gravity and the speed of light very tightly indeed. Now, that good sky localization with Virgo added to the network allowed us to pinpoint the galaxy where this event happened. That was actually done by optical telescopes within a few hours of the gamma ray burst and the gravitational wave event, and the galaxy's name is NGC 4993, not a particularly exciting galaxy, but this was certainly a very exciting event because you can see the before and after photo. The black dot in the photo on the right is this new object, this aftermath of the neutron star merger that we call a kilonova, that was detected by many telescopes around the world and opened up a whole rich vein of astrophysics research to try and understand what really goes on when 2 neutron stars collide. From my point of view, what it was incredibly useful for was providing a wholly new way to measure the expansion rate of the universe, what we call the Hubble constant, and I'll talk a bit more about that in a few minutes. And that's because we could get a distance from the gravitational waves, and then we could get the redshift of NGC 4993, and then combine the distance and redshift in a manner you're probably already familiar with if you've had talks before or read about how we measure the Hubble constant, measure the expansion of the universe. but this was a new way to do it, not relying on observations in light, but using gravitational waves, at least not for the distance part. So the next milestone was in 2018, we published our first catalogue of gravitational wave events. So this was beginning to mark the transition where we were less concerned about individual objects and about what we might say about the properties of the whole population of gravitational wave events. Maybe a bit like what's happened in other fields as well, maybe something like exoplanets where, exoplanet discoveries are interesting in and of themselves, but what's really starting to get interesting is the picture we're building up by observing hundreds, indeed thousands of them. So that's the process that's been unfolding in recent years. This first catalogue only had 11 events, 1 neutron star merger and 10 black hole mergers. But it wasn't too long before we were collecting many, many more detections. Our third observing run began in April 2019, and that ran through to March 2020. And we observed a number of events, which I'll highlight in a moment. Another interesting aspect of that third observing run is that we were releasing candidate events, details of candidate events, just on the internet to anyone that was interested. Instead of just communicating that information to professional astronomers, you could actually install an app on your phone and just get alerts directly to your phone using this app called Chirp that our colleagues at Birmingham University created. So here's a little chart of how the number of events really shot up during that third observing run. By the time the third run had ended, we'd accumulated a total of 90 confirmed gravitational wave events. And we published a catalogue of those events in November 2021, just over 3 years ago. Now here's just a couple of examples of events that we saw. So one in April 2019 was interesting because it was a big black hole and a much less massive black hole. And what that gives you is a richer pattern of gravitational wave signal. A bit like if you've got a chord in music, you get extra harmonics in the frequency pattern of the music sound. So it's a richer sound, it's a more interesting sound. So similarly, the gravitational wave pattern that we detected from this event, 1904-12, was richer because of the imbalance in the gravitational masses of the two black holes. And then a bit later that month, we detected another collision of neutron stars. So we think they were neutron stars based on the lower mass of the two objects that merged. But actually this time we didn't see a gamma ray burst. There might well have been one, but the event was much further away than the event in August 2017. We got really lucky in August 2017, to be honest. This one was much more distant and it wasn't so well localized on the sky. So finding the host galaxy of the neutron star collision was not going to be possible. One way to kind of get a sense of the fact that the signal was not so strong, well, what I'm doing there is putting a curve to map out the chirp-like pattern in the time frequency plot, and you can maybe just about make out behind that. In fact, maybe I'll just go back so you can see that what I'm running is an animation where I'm including the signal and then subtracting the signal. And it doesn't really look that different by eye, but with our statistical tests, we could really definitely confirm a detection, and it's maybe helpful just to kind of guide your eye in that manner. But if we contrast that with the one in 2017, that was a much, much clearer track in the data because it was much closer and it was a louder signal. But this event was still interesting because the masses of these neutron stars were more massive than typical neutron stars in our own galaxy. So that's what the graph in the top right is showing. So you've got a little histogram, which is the galactic neutron stars, things like the pulsars that we detect in radio, like say the Crab pulsar, that was such a significant event detected by Jocelyn Bell back in 1967. But the neutron stars detected in gravitational waves are shown in the right-hand graph, and they're really quite distinctively massive compared with the galactic one. So that's an example of the kind of thing that we're now embarking on, is trying to understand theoretically why gravitational waves can probe a sort of different part of the neutron star mass population than electromagnetic observations. and building up a bigger and better picture of neutron stars by combining information from both electromagnetic radiation and gravitational waves. The next one to mention was in May 2019. This was a really massive black hole. The merged black hole was nearly 150 times the mass of the Sun, making it the first example we detected of what we call an intermediate mass black hole. So the two progenitors that merged together were pretty massive beasts as well, and you can see that in the graph. And what that indicates is, well, some quite interesting possibilities as to how this system came to be. So, for example, it's quite likely that the two black holes that merged, one 85 times the mass of the Sun, the other 66 times the mass of the Sun, themselves were the result of a merger of two smaller black holes. So we didn't see those earlier mergers. But the thing is, it's pretty unlikely that you would get a black hole as the remnant of a core collapse supernova as massive as 66 and 85. So what's more likely is that you maybe get core collapse supernovae giving smaller black holes which merge together and then merge again to ultimately give us this one with a whopping 142 times the mass of the Sun. And that's not such a crazy idea, because the idea of hierarchical mergers would generally fit in with a picture of how black holes might evolve to ultimately give you supermassive black holes, such as we believe are present at the hearts of pretty much all galaxies. Those have got masses of millions or even billions times the mass of the Sun. Well, how are you going to make them? Well, one part of that story might well be merging together smaller black holes. So perhaps that's what we were seeing here. There was another event in August 2019, which was another example of a much more massive object and a less massive object. And this time, we actually weren't sure if the less massive object was a black hole or a neutron star. More likely a black hole, but we can't be sure. But again, like the one in April of that year, it gave a very rich pattern of gravitational waves from all the extra frequency information, all the extra harmonics that you get as a result of the mismatch in mass. And here we can see just a little bit of that. We can see that the what we call the higher multipoles of the emission, you can think of them as, just as I said, a bit like the harmonics, the extra harmonics you would get in a rich chord played on an instrument like a piano. So that just about brings us to the end of the third observing run, but there was a bit of a sting in the tail early in 2020. We actually got two events just a few days apart, both of which we were much more confident was a black hole merging with a neutron star. Now this, of course, is just an artist's impression. It's from our colleagues in the Australian gravitational wave groups called OSGRAV. I think it looks really splendid, but we don't know in detail exactly what these systems would have looked like, but we could measure their masses quite precisely, and they much more confidently could be categorized as one black hole and one neutron star. So we published papers about these mergers. We ran simulations to try and capture the detail of the gravitational wave signal you'd expect from systems like this. And in fact, there were two different scenarios. So one is where the gravitational wave signal is quite interesting and quite rich in its harmonics, but it corresponds to the black hole gobbling up the neutron star more or less in one gulp. That's what we're going to see in the animation in just a moment. So the neutron star is the big orange blob, and you'll see it's going to be swallowed up by the black hole in one go in just a moment. Meanwhile, you could also have a scenario whereby I'll just run the top one again, so that's playing while the lower one is also playing, where the neutron star is shredded by the tidal gravity of the black hole. So it gets torn apart, and what you get instead is like a disk of material around the black hole, and that would likely give some accompanying electromagnetic radiation from what we call the accretion disk. It would also change in subtle ways the gravitational wave pattern as well. So long story short, the two events that we saw in 2020 look much more like the top animation than the lower one. We didn't see any evidence of the neutron stars getting shredded, but what we saw was consistent with the black hole swallowing the neutron stars in one gulp. Or as I like to put it when I'm talking about this in outreach, it is sort of more the case that the black holes were acting more like Pac-Man than Cookie Monster. Pac-Man would swallow the neutron star in one gulp. Cookie Monster's a notoriously messy eater, so the neutron star's guts would be spewing around the black hole, torn apart. Now, if that were to happen, that would be incredibly interesting scientifically because it would give us insight into the internal structure of neutron stars and sort of how rigid the neutron star is, how willing it is to be torn apart by the black hole's gravity. So we certainly want to see more systems like this in the future, and it would give us a window into the interiors of neutron stars that's, again, quite mind-blowing to think that we could learn something about that environment. So, as I said, we published this catalogue of 90 events in November 21. That's represented just by a kind of visual picture here. You can see lots and lots of events, one or two with lower masses, that's down towards the bottom of the figure, and lots with quite higher masses, around 20 or even many more times the mass of the sun. We've done a lot with these data. Let me just spend a little bit of time on that. I'm minded, I don't want to overstay my welcome. If I talk for about another 10 minutes, would that be okay? I don't want to talk for too long, but if that fits in with your timings, then let me just say a few words about some of the things we've learned. So this looks quite complicated. Essentially what it's capturing is the ways in which we've been able to test if general relativity seems to be the correct theory. So what we've done is compared the actual final mass that we measure with the mass predicted from general relativity. And if those two match, then what you should basically get is a value of 0 in this plot. So we don't get exactly 0, but it kind of hovers around 0 pretty closely. And in fact, it's improved a lot as we've got more and more data. That's what you see is the kind of sharpening up from the red curve to the blue curve. So long story short, all of that means that Einstein's actually pretty happy that general relativity thus far seems to be passing the test, that it is a good description of how gravity really works. So let me just spend another couple of minutes talking about how we've used gravitational waves to try and measure the Hubble constant, the expansion rate of the universe. So remember back in Laura's video, she talked about how you can estimate the distance. So that's the key step, is to get the distance from the gravitational waves, combine that with the redshift that you get from electromagnetic observations. So for the very first opportunity to do this, we looked to the neutron star merger in 2017. Again, a lot of detail in this slide. If you're into the numbers, you might know that the Hubble constant has been measured to be around about 70 in the rather weird units of kilometers per second per megaparsec. But if you don't want to focus on the numbers, just look at the graph. What you see in the graph, well, it peaks around about 70. That's our measurement. And that's in the same ballpark as measurements using more traditional electromagnetic methods. So those are represented by the vertical green and orange bands. But the crucial point is those green and orange bands don't overlap. They don't agree with each other. As many of you will know, we're facing a bit of a problem in cosmology, what people call the Hubble tension, where different methods to measure the Hubble constant give inconsistent answers, and we're kind of left scratching our heads a bit as to what's going on. So the hope is that gravitational waves might help to resolve that Hubble tension. We were never going to do it with just a single detection, but at least our number was in the right ballpark. It was essentially in agreement with both sets of electromagnetic-based methods. So what's happened since then is that we've gone about trying to improve things, and we've gone about that by using the black hole events as well. Now that's a bit tricky because we don't know which galaxy the black hole merger is in to get the galaxy redshift. So what we have to do, the method is called the dark siren method, is that we've got to look at all the potential host galaxies from our ability to kind of localize in the sky where the gravitational waves are coming from, and sort of average, or the technical term is marginalize, over all of the redshifts of those potential host galaxies. So there's a bunch of papers that we've written doing exactly this, and essentially what that's led to is a slow improvement in our estimate of the Hubble constant. So firstly, in 2019, we sharpened things up from the orange curve to the blue curve by adding in some extra black hole mergers and doing this averaging trick to get the redshifts. And then more recently, well, just to note in passing, that even though there was a slight improvement doing that, the result was still dominated by the neutron star value that we got in 2017. But the most recent result we've published is sharpened up a bit more, and it's kind of tempting to say, oh, that looks like it's homing in on the lower value of the Hubble constant, which is what we seem to get from things like type 1a supernovae and Cepheid variables, but it's really too soon to say. Our hope is that in the next few years that we will be able to say something a bit more definite about what Hubble constant we're getting from gravitational wave sirens rather than the traditional electromagnetic methods. In fact, if I try and summarise all that, since about 2000, these different values for the Hubble constant have been emerging by different methods. That's represented by the blue and the red bands. You know, they don't agree with each other, and we're not really sure why. So our original 2017 estimate has the really big uncertainty, a big green vertical line, which was straddling both the blue and the red bands. And what we really would like is to get something like about 15 of those bright sirens, or maybe equivalently a few hundreds of the dark sirens, the black hole ones, which aren't quite so precise because we don't know the host galaxy. And that might start to give us insight as to whether the Hubble constant really is sort of the higher value, the lower value, or as luck might have it, maybe somewhere in the middle. So watch this space. By another few years, we would hope to have made some progress there. So that really brings me to the very final bit of my talk, just the final few minutes, to give you some insight into what maybe will happen next. So our fourth observing run began on May 24th, 2023. And as you can see, by mid-December, we'd accumulated more than 250 events today. So that's all the ones that we've confirmed so far, plus also a bunch of candidates that we're still analysing. So we've confirmed one event from our fourth observing run. That's quite an interesting one. It's called 230529. The names just indicate the date on which the event occurred. And this is interesting because it's a black hole in a neutron star, but the black hole is actually quite a low mass black hole. It's in the region that has sometimes been referred to as the lower mass gap, because what we had thought was that, well, you see neutron stars up to a certain mass of about 3 times the mass of the sun, and then the lowest mass black holes that we've been able to infer from like X-ray observations and things like that seem to begin at about 5 solar masses. So there was a suspicion that maybe there was a gap, some reason why nature didn't produce black holes between 3 and 5. But that doesn't look as if it's true, because it's just now that we can use gravitational waves to probe that so-called gap, and we discover that it's not a gap at all, that there are black holes in that mass range. Looking ahead towards the end of the decade, we'll complete our 5th observing run, and the gap in between will involve more upgrades to improve the detectors, and that will hopefully get us to a point where we're detecting events pretty much multiple events every single day. So that will rapidly give us many hundreds of events, which, as I said, will hopefully start to give us some leverage on resolving the Hubble tension, as I was describing a few minutes ago. What about beyond that? Well, into the 2030s, we want to build even more sensitive detectors. One way to think about that is that what we're observing right now is roughly out to a redshift of about 1, or a look-back time of a few billion years. I mean, that's a long way into the universe, but it's a long way short of, for example, the time when the first galaxies were forming, the kind of regions that the James Webb Space Telescope is now looking at in infrared light. So what we would like is to have detectors that can probe that far back to redshift 9 or 10, to the very earliest galaxies, to the very earliest collisions of black holes in those galaxies. So on the ground, there are facilities under development. We're not actually building them yet, but we're doing a lot of the preparatory work and trying to get the funding. So one is a European project called the Einstein telescope. There's a US equivalent called the Cosmic Explorer. And those will improve the sensitivity by another factor of 10 compared with the Advanced LIGO in 05. And that will give us maybe 100,000, maybe into millions of events every year. So this will really be a game changer in terms of letting us answer a lot of the questions that we're just scratching the surface on right now. And then just to finally give a context for me wearing my LISA sweatshirt, the other thing that we would like to do is to probe more of the gravitational wave spectrum, just like we're able to probe the electromagnetic spectrum, as my very early slide showed. And right now, the ground-based detectors are only really able to get down to a few hertz, a few cycles per second, because gravitational waves with lower frequency than that, we just can't detect them on the ground. They get swamped by all the seismic disturbance, the shaking of the detector. Not too bad at higher frequencies, but really too bad below a few hertz. Einstein telescope might get us down to about 1 hertz, but below that, we've really got to go into space. So if we want to observe lower frequency gravitational waves than that, we need spaceborne detectors, and that's where LISA comes in. So LISA was officially approved just about a year ago on the 25th of January 2024 as the next big flagship mission of the European Space Agency. And it comprises 3 satellites, 2.5 million kilometres apart, orbiting around the Sun in a triangle behind the Earth, bouncing laser beams back and forth. So the interferometry part is broadly similar to what LIGO does, looking for changes in the separation of the satellites as an indication that a gravitational wave has passed by. And the kinds of events that LISA will observe will include supermassive black hole mergers, possibly out to redshifts of 10 and higher. And there's a decent chance that those actually might be accompanied by electromagnetic radiation, not coming from the black holes themselves necessarily, but from the accretion disk around the black hole, the kind of environment that you see in things like quasars, for example, or active galaxies. So if that were to happen, then it might give us the chance to get fresh insight, not just into the Hubble constant, but how the universe is apparently accelerating, the speeding up and the expansion. Now, you might be aware that there was a paper published just in December that's actually challenging that whole notion of the accelerated expansion of the universe. Now, I've not really had time to get my head around this. It concerns really challenging the notion of dark energy as this kind of almost like anti-gravity pushing the universe apart. I mean, dark matter is mysterious enough, but in the last 20 years or so, we've come to see that the best way to describe the universe appears to be a mixture of dark matter and dark energy, the dark energy driving this accelerated expansion. So I'll be spending some time next week at a workshop in Poland trying to get my head around this paper published in December that's about what's called the timescape cosmology model, that's basically saying, oh, you don't need dark energy after all. I'm not sure if I believe this, but it's an indication of how little we really know yet and how much more there is still to do. So in the 2030s, our hope is that LISA, combined with some really advanced ground-based facilities in electromagnetic radiation, things like the extremely large telescope in Chile, operating in the optical and infrared, combined with, say, the square-kilometre array radio telescope in Australia and South Africa, all of that together might finally start to help us get our heads around what on earth is really going on with dark matter and dark energy. Is the universe actually accelerating in its expansion? If so, why? And is it something just like the so-called cosmological constant, or is it something more exotic than that? In fact, it could even be an indication of extra spatial dimensions. A couple of years ago, I wrote some papers on this with colleagues indicating how LISA might be able to constrain the number of extra dimensions if it's the case that we've got those extra dimensions that gravity can propagate through, but electromagnetic waves can't. Now, that's a pretty wild idea. I'm not saying I believe it, but for decades it's been talked about theoretically, and it will be very interesting to get to a point where we can actually start to test it observationally. So that's coming in about 10 years and beyond, with the launch of the LISA mission. So I hope in this talk, and I hope, again, I've not overran too much, but there's a lot of ground to cover, both the exciting past decade, but also a little bit about the excitement that lies ahead. And while we might be probing the dark side of the universe, I hope I've convinced you that gravitational wave astronomy has got a very bright future. Thank you very much.
Martin, thank you for an absolutely fascinating talk. What a brilliant way to start off our year. Thank you very much. I'm just going to go to questions and hopefully some answers.
Yeah.
Back to gallery so we can see everybody. A lot of information there, Martin. I'm going to have to go and look at this again. So, as usual, ladies and gentlemen, if you've got a question online, come have a digital hand. If you're in the room, try to attract my attention, and we'll take it from there. So, starting off with Mike Scollin in the room.
Good evening, and thank you again very much for the talk. Does the density of the medium affect the propagation speed of gravitational waves? And could that be the difference between the arrival times?
It's a great question. I mean, it could in principle, but the thing is, space-time is unbelievably stiff. It's one of the reasons it took us 100 years to develop the technology capable of detecting gravitational waves. Like, strictly speaking, when I shake my hand like this, I'm generating gravitational waves because I'm changing the local curvature of space-time produced by the gravitational field of my hand. But of course, it doesn't weigh very much, and I'm not moving it close to the speed of light. So, in principle, yes. And, there's analogies there with the way that electromagnetic waves are affected by the density of the medium as well. It's no accident that gravitational waves are predicted in relativity to propagate at the speed of light. So there's a lot of crossover between, relativity as it applies to light and relativity as it applies to gravity. But the key difference is that because space-time is so unbelievably stiff, then frankly, gravitational waves will just barrel on through the universe as if there's nothing there. And that's A, what makes them incredibly hard to detect, but B, in a way, gives us the chance to see gravitational waves from environments where light just wouldn't make it out, because it would get scattered or get absorbed by the intervening medium. So it's a classic thing. It's a bit of a challenge to understand the kind of subtle theoretical differences, but it's also a big opportunity. One of the areas that I work in with colleagues at Glasgow and other institutes around the collaboration is to look for evidence of what we call gravitational lensing. We know about that for light, the bending of light beams by the intervening matter, and we believe that that could happen with gravitational waves as well. But again, there are some subtle differences as to the kinds of situations in which it would occur. If we observe that, that would be immensely valuable information. It might give us insight into dark matter, for example, all sorts of things like that. So again, watch this space. But you're right in principle, but in practice, because space-time is so stiff, then really that information is, it's sort of like below the radar, if you like. There's really nothing that gravitational waves will typically pass through which will affect the arrival speed. Certainly not that 1.7 seconds that you see with the delay between the gamma rays and the gravitational waves.
But could we say that the speed of gravitational waves is the constant and the speed of light is something that varies slightly depending on the medium?
That's one way to look on it, but I think there's a sort of deeper level concept going on. There's some really good YouTube videos on this. Well, I mean, there's papers on it too, but I think some really, really excellent examples of top-notch science communication from Matt O'Dowd that runs the PBS Spacetime channel. So it's a show on PBS in the US, but they're all on YouTube as well. And he's got a video talking about the speed of information. So in some sense, this is tied up with the notions in GR of causality, the fact that only when you're within what's called the light cone can you have events causing other events. Now, of course, the complication is that GR isn't the final story either, because we know that in quantum physics that causality doesn't quite seem to behave like that either. So the reality is probably something even weirder that will take the form of quantum gravity, but we're a long way off having a theory of quantum gravity. And the kind of LIGO observations I've talked about aren't really in a regime that could inform a theory of quantum gravity. Maybe Lisa will start to chip away at that. But again, these are all examples of the kind of mysteries that we hope to shine some light on, or some gravity on, in the years to come. Thank you. Great questions.
Okay, thank you, Mike. I'm not seeing anybody else. I think you've stunned everybody to
Yeah.
quite silence. Oh, Roy Stewart, online.
Hi, Martin. Can you hear me?
I can, Roy. Yes.
A fantastic talk. Thank you very much. I'm not sure if my question is very similar to the previous one, but gravitons have been postulated as a hypothetical particle. Do you think these observations will go any way to sorting out this problem out?
That really follows on very nicely from the previous question, Roy. So thank you. I mean, I was just kind of touching on that at the end. I was saying that, thinking about how gravitational waves and light propagate through the universe, we can sort of do it within the framework of GR, and that takes us so far. But we know that GR isn't really the full story either, and that there ought to be a sort of a deeper theory of quantum gravity. So the graviton would be associated with that. And the truth is that at the moment, our gravitational wave observations are not really probing that regime yet. It's a bit like how radio waves can be very well described by just wave theory of light. You don't need to think of them as quantum. Whereas if you're talking about ultraviolet radiation, or even light, visible light to a large extent, you do need to think of the quantum aspects. So as you go to higher frequencies or shorter wavelengths, then the quantum aspects become more and more important. And we're not really into that quantum gravity regime yet, but we would hope to with future observations. It's a combination of probing higher frequencies to begin with, but also just having better data so that you can tease out the very subtle differences that the graviton would introduce. I mean, way back in something like 2009, I was external examiner for a PhD from a student who's now, a very kind of senior member of our collaborations, who was just beginning to look at this. It's what would the existence of a graviton mean about the gravitational waveform? What would it look like? How would it differ from if there isn't a graviton, or if the graviton has got more mass or less mass? So these are the kind of questions that we just don't have good enough data for yet, but we are starting to do the theoretical work. In fact, we've been doing it for maybe 15 years or so. So we've got to wait a little while until the instruments catch up. And again, we've been there before, because if you look at, say, our cousins in particle physics, Peter Higgs predicted theoretically the Higgs boson 50 years before that was detected. So they had to wait 50 years. Maybe we won't have to wait quite that long, but that's sort of where we are right now.
Brilliant. Thank you very much.
Thank you, Roy. I'm still looking for questions. I can't see any. Anybody in the room? No.
Well, again, I hope that isn't a sign that I was, taking on more than biting off more than I could chew, but I did cover a lot of ground. Let me assure you that, given that you were recording it for YouTube, if you do want to follow up with any questions afterwards, you've got my contact details. Don't hesitate to get in touch. I'll be very happy to try and answer any questions that occur to you later.
Martin, that's very generous of you. Ladies and gentlemen, will you join with me in giving Martin Hendry a huge Mexican Institute in Astronomical Society? Thank you. Thank you very much, sir.
All the best. Thank you.